Yeah. Does that make sense? Yeah. Okay. Any other questions about this stuff before we get started? Homework? Yep.
It's different problem.
Okay.
17 and 24 in 3.3.
17 and 3. Oh, hold on. Sorry, my brain just like dropped the gear.
Oh
there.
yeah, no worries.
17 and
24 in 3.3.
3.3. That's the wrong book. 3.3, 17. Verify the path given as a flow line. Okay. X of t is sine cosine 0. And f is x minus y 0. Okay, so what does it mean to be a flow line? Is it a differential equation that describes what it means to be a flow line, right? So you're a flow line if x prime evaluated at t is equal to f, I guess we would say the gradient of f evaluated at x of t. This is the equation of what it means to be a flow line. So you're a flow line if your derivative, your time derivative of the flow line, so the velocity of the flow is equal to the gradient of the vector field that the flow is happening. So this is just a definition of what it means to be a flow line. So we can just check and see what that means.
So is that a vector field?
This is a vector field right here. Yeah.
Okay, so the gradient of that vector field.
Yeah. Is it grad F? Oh, no, this F here. Sorry, this is supposed to be little f, right? It's the gradient of the potential field, but the gradient of f is the vector field. So it's f of x of t. My bad. Sorry, that was confusing. We think of f as being the function that comes from taking the gradient of a potential field. Okay. And so you can just plug this in and see. I mean, what's x prime of t? X prime of t is equal to cosine t minus the sine of t 0. There's x prime of t. And then if we take x of t and we plug it into f, well, f of x of t is equal to f of, well, what is x of t? Sine t, cosine t 0. And what does f do to that? It leaves x alone. It takes the negative of the y.
Where'd you get that x negative y from?
What's that?
Where'd you get that x negative y 0?
That was given a problem.
That was y negative x.
Is it y negative x? Oh yeah, no, wrong. I was doing problem 17, which is y. Sorry, right. Y. I would have noticed when my answer was wrong. Which it is. Okay, yeah, that's the wrong f. Okay, so just imagine I didn't do that. So what does f do? F takes the y and puts it first. F takes the x, puts a negative on it, and puts it second. F leaves z alone. And this are equal, which means it satisfies the flow equation. So it's a flow line. That's all there is. These are questions. So we computed x prime of t. We computed f of x of t, and they are equal to each other. And that's what it means to be a flow. They're equal to each other for all t, and that's what it means to be a flow line.
Yeah, how can you draw it?
Draw it? I mean,
I know it's like circle.
well, let's see. Let's just start putting some points into f and see what comes out, right? So if I put in 1, 0 into that f right there, 1, 0, 0, right? The z coordinate of that field is always 0. So I'm just going to match. I'm just going to draw a 2D picture of this. I put in the point 1, 0, 0. What vector comes out? I put in 0, 1, 0. What vector comes out? Let me get this right. Hold on a second. If I put in the point 1, 0, 0, I get out 0 minus 1, 0. Okay. And if I put in 0, 1, 0, 0, I get out what? That's weird. Really? I messed something up. F of 1, 0, 0 is 0, -1, 0. And f of 0, 1, 0. Oh no, I was drawing in the wrong spot. You're right. Yeah. So f of 0, 1, 0 is equal to 1, 0, 0. So this goes like this, and this points this way, and this points over here. Oh, it's going to be a swastika. Not do that. Let's I don't know what it is with these. Yeah, okay. F of 1, 1, 0 is going to spit out 1, -1, 0. So if I, at this point right here, I'm pointing this way and that way. So I'm kind of like this. And then I point this way, and this way, and this way. I'll just make it a stop sign so I avoid the. But this is what the vector field does, is you draw the arrows around. And so what you should see is as you go around the different points, you're always going to get these sort of 2D vector. So I'm restricting myself to the case where C is equal to 0, right? Just so I get a picture of what's happening here. And what the flow lines are telling you is, if you're at a particular point on this curve, the flow line is telling you that you move like this. Does that seem like it accords with what the vector field is doing? Yes, yeah. Right. The idea is that any point on the circle, the tangent line of the circle path is equal, the velocity of this path is equal to the flow line from the vector field. That's how I would sketch it.
I thought you had to sketch like in 3D.
No, man, you guys are crazy if you want to sketch in 3D. No, don't do that. I mean, you can, if you really want to, but I don't know how to draw a vector field in 3D. If you really want to visualize vector fields in 3D, you should come ask me how to work with Math 3D. It's very straightforward. It's actually quite enlightening to look at these things in 3D. If you put this vector field into 3D, what you get is this giant cylinder vector field where it's all sort of doing this, but like stacked up in the z-axis. So it's like everything is swirling around the z-axis like this. And what you're saying is, as you drop any point in anywhere, you're always stuck in the same plane. You have to swirl in the same plane. Now, if I was going to try to draw that, I would probably cop out and draw something like, oh yeah, here they kind of do this, and they go around, and then here the flow lines go around, and here the flow lines go around. And I wouldn't even bother trying to draw the vectors because good luck. So I think some worried people have already asked me about like what happens on an exam with vector fields, and the answer is I promise that if I ask you to work with a vector field, I will draw it for you. I'll give you the functions, you can do the calculus, I will draw you the vector field. Okay. You already took 241 to get in here. You don't need to draw more vector fields. All right, what else? 24. Consider, okay. This is a central question here. So 24 was assigned to you guys because there's a central question, which is the nicest vector fields arise as gradients of potentials. And so the language I want you to remember here is a potential is just a scalar field. So F acting from X in Rn into R. And then there's the vector field attached to it, or the gradient field. So potentials turn into gradient fields by looking at capital F, which is the gradient of little f. And those take Rn into Rn. And so if you start with a gradient field, sometimes they come from a potential. To say that a vector field is a gradient field is to mean there is some f that it is the derivative of. These are sort of the things you could integrate if you wanted to. And they're the central objects of physics, actually, vector fields that you can integrate. So if I give you a vector field and I say f is equal to 2x plus 2y minus 3. And I say, boy, oh boy, it sure would be nice if you tell me what field that came, or what potential function that came from. Even if you don't know, in order to be true, it would need to be the case that the gradient of f. No, let's not even do it that way. Let's just eyeball this. Is there any way that I can think of? What's the easiest function I can think of that if I took its derivative with respect to x, that 2x would fall out? Squared. How about x squared, right? Okay. And oh, I guess this is supposed to be I, J, and K. That's part of the problem here. There's a J, there's a K here. This is 2x, 2y minus 3. But if it's a gradient, that means this is supposed to be fx, fy, fz. The derivative of this function with respect to x is supposed to be 2x. So if you do a partial integration to get f back again, you get x squared. Where did the 2y come from? Well, if fy is 2y, then f had better be equal to y squared. And this minus 3 out here, the easiest thing that could have come from is. Okay, so as soon as you write that down, you've exhibited that f is a gradient field because you found the function that it's the derivative of. Right? So this is the potential for f, which is 2x, 2y minus 3. And that means this is a gradient field. What is the rest of it? Describe the equipotential surfaces of f with words and with sketches. Now, if it was me, what I would do is I might go to Math 3D and punch it in and see what will happen. If you're really good, though, if you're really good at thinking about what equipotentials are, remember that an equipotential is just a level surface. Equipotential is a fancy word for level surface, which means you just set that function equal to a constant. What is this? If I write down x squared plus y squared minus 3z is equal to 0, what is this? Can't be a cylinder because there's z here, yep. Well, there's not a hand up, it's hand twisting. It's a paraboloid, right? It's a paraboloid. It looks like this. It's a paraboloid. And if you change the constant here, what you're doing is you're taking that paraboloid and sliding it up and down. So every level curve of this function in 3 space, the places where the values are constant are these paraboloid shapes. So in cross section, what you'd be saying is space is cut up into shapes that look like this, where the values of the function are constant on all these sort of parabolas, but it wraps in 3 dimensions to do that. So there's shelves of equal value. Okay. All right. Okay. Now I'm going to talk about Hessians. Make sure this is recording. I'm paranoid now that I've lost one of these. All right. Well, hey guys. Okay. So last time we talked about, I briefly scared everybody by reminding you that eigenvalues existed. And I pointed out that in 2 variables, so this is 4.2. So this is about extrema. So what I pointed out about extrema was that you guys learned a theorem when you did 241 or wherever you took your multivariable calculus that said that there's a theorem that says critical points happen, local maxes and mins happen at critical points. And then we use some math to show that we can actually use the second derivative test. We can use the first derivative to find critical points. So whenever df is equal to 0, we have critical points. And I left off with the idea that we can use the second derivative. HF classifies critical points. And I made the point of saying that there's this function running around the background called the quadratic form. You don't actually need to know much about that except that it lets you take the behavior of a, so HF here, this is the Hessian matrix. HF looks like fx. In the 2 variable case, it's fxx, fxy, fyx, and fyy. That's the Hessian matrix, right? And the idea was this matrix encodes all of the curving behavior of f. Not just in the x direction and the y direction, but in all the directions in between too. What's up?
What's the sign like this number 4? No, like just right of number 4. Like
Oh, HF, Hessian of f.
oh, okay,
Isn't DF a matrix?
Yes,
So how come it equals zero? Like
if
all
it's
the-
0 in each entry. Right, so what we mean in the two variable case is that fx, fy is equal to 0, 0.
Oh, yeah. All the-
Yeah, everywhere where the first derivative is equal to 0 and also the second derivative, sorry, everywhere the x derivative is 0 and also the y derivative is 0, those are the critical points. So solving these equations give you the critical points, and I'm going to show you how to use the Hessian matrix, HF, to figure out what kind of point we're looking at. Now, what you guys learned in the old days, whatever, like old days of 3 months ago for some of you, is that you can define this quantity called B, which is fxx times fyy minus fxy squared. So the two variable case, you learn this is the second derivative test. If your teacher did a good job anyway, you learn this. And you learn this sort of weird test with a lot of cases that said, if D is positive and fxx is positive, then a critical point is a local minimum. And then you learn if D is positive and f of xx is negative, then you're at a local, then the critical point is a local max or local maximum. And you also would have learned if D is negative, you're at a saddle point. And if D is equal to 0, then it's unknown. So this is usually the way this is taught to 241 students, is this weird pile of cases. And I want to point out, first off, this idea, the way that I think I told you guys I wanted you to read Colley's explanation because I found it amusingly terrible. I hope she's not listening here. But the reason why it's so technical and hard is because she's trying to avoid referring to eigenvalues. Okay, so this quantity right here is the determinant of the matrix fxx, fxy, fyx, fyy. And it's actually equal to the product of the eigenvalues of that matrix. Right? So it's lambda 1 and lambda 2, where lambda 1 and lambda 2 are eigenvalues. The eigenvalues must exist because the matrix is symmetric. So what are you really testing here? If this is positive and the first eigenvalue is positive, then both of the eigenvalues have to be positive, right? If the product of the eigenvalues is positive and lambda 1 is also positive, then they were both positive. So this condition, all of this checking for a local minimum is checking lambda 1, lambda 2 is positive, and lambda 1 positive implies that lambda 2 is also positive. All the eigenvalues being positive means that the matrix curls that surface up in every possible direction. That's what it means to be a local minimum. So if the eigenvalues are positive, I'm not going to ever make you do this, by the way. I'm going to have you punch this into a computer. I'll tell you the eigenvalues. The Hessian matrix has these eigenvalues at these points. Interpret the result. Okay. So this corresponds to the case where, oh, well, now if the determinant is positive, well, the determinant is equal to the product of the eigenvalues, and one of them is negative. So if the product is positive and one of them is negative, then the other one has to be negative too. Negative times negative is positive. This corresponds to the surface bending down in every direction. Yep. It's supposed to be local min, yeah. Positive means you're bending up in both directions. I very well at the very end of blasting through it could have written that incorrectly. Yeah, so you should think positive curvature in the same way that like positive derivative in the second, concave up means this. This is really a measure of concavity. The eigenvalues are telling you the concavity. So if the eigenvalues are both positive, means you're concave up essentially in all the curvature is concave up. Yep.
So those eigenvalues are fxx.
Okay. So somewhere in your 206 class, or 244, what you would have learned is again, depending on what your teacher was, you were supposed to have seen this. A 2 by 2 matrix that is symmetric, this is symmetric because these are equal, always has 2 eigenvalues. They might repeat, but there's 2 eigenvalues. And so you can do a diagonalization. This matrix also can always be written as a matrix times a diagonal matrix that looks like lambda 1, 0, 0, lambda 2. So we're not doing a bunch of linear algebra. I'm just reminding you that these are change of basis matrices. You probably saw those. This is kind of technical, but the basic idea that really mattered here was a symmetric matrix can always be written so that you've got this diagonal matrix in here. And the determinant of a symmetric matrix is the same as the determinant or the product of its eigenvalues. Right? The determinant of a matrix is equal to the product of the eigenvalues. That's one of the central things you were supposed to take away from linear algebra. That we want to take this complicated study of functions and turn it into the study of a matrix. Colley is also turning this into the study of a matrix, but her approach is never to tell you about eigenvalues, make you do it all with determinants.
So eigenvalue 1 is not the same.
Not necessarily, no, because they are not the same. No, they're definitely, in general, they are not going to be the same. You're going to get some numerical matrix here, and you go off to, if you take a numerical matrix and you put it into Wolfram alpha, it will tell you what the eigenvalues are. I just tell you what it diagonalizes into. I'll give you the eigenvalue. Well, you would have to figure out what the Hessian matrix was, and then I'll tell you how to. I'm going to give you enough information to interpret it. I mean, you know the function. You have the f. You could compute the Hessian matrix. So I would tell you a question like, "Here's f. Find df, and use it to figure out what the critical points are." Okay, there you go. Then I would say, "Here, compute hf." Once you've done that, I'm going to tell you what the eigenvalues are for the critical values that you've already found. I'll tell you what they are. But the idea is you might have to compute this matrix, but I'm going to tell you what this one is. I don't want anybody in here doing the determinant of a minus lambda I and computing characteristic and polynomials and factoring it. The point is, from a computational perspective, analyzing maxes and mins boils down to something you can tell a computer to tell you about a matrix. That's what I care about. And from a theory standpoint, what you're doing is you're saying the matrix measures the way the surface curls, all of its curvature. It's not enough just to look in the x and the y direction because there might be saddle point stuff happening in some different direction. But the matrix will tell you what's going on. The saddle point corresponds to, well, if the derivative was negative, that means that either lambda 1 was positive and lambda 2 is negative, or lambda 1 is negative and lambda 2 is positive. And that means it bends up in one direction and down in the other one. That's what it means to be a saddle point. So this sort of corresponds to shapes that look like this. This corresponds to things that look like this. And this corresponds to that sort of weird case where you had I like parabola, hyperbola. There we go. Like that. Right. But that point right there is the saddle point because it bends down in one direction and up in the other. Okay. And then if d is equal to 0, we can say nothing, just like in the one variable case where if the function is too flat, the second derivative has no information inside of it. So how does this work in n variables? Now, if anybody really wants to, I can tell you how Colley wants me to do it. But I wouldn't do it that way. I would do this. I would say, okay, finding local maximum. For an n variable function. First off, we already know that the second Taylor polynomial for these guys looks like f of a plus bf at a plus 1/2 times x minus a transpose hf at a x minus a. That is the Taylor polynomial that we're using all this out of. If hf, okay, so critical points, step 1. Critical points when df is equal to 0. All points x and y where that derivative matrix is equal to the 0 matrix. 2, if A is a critical point. We have three cases, just like these. If all of the eigenvalues of H, F, and A are positive, then the surface is concave up in every direction, and you're at a local minimum. Now, granted, that's not what an n variable surface looks like, but that's the way you should think about it. Yep.
In that equation, there's supposed to be an x minus a.
There is supposed to be an x minus a. Thank you. Yeah, to locate the tangent plane. Okay, if all the eigenvalues of this matrix are positive at a given point A, then A is a local minimum. If all of the eigenvalues of H, F, of A are negative, then you're concave down in every direction. And you're at a local maximum. If eigenvalues of H, F, of A are a mixture of positive and negative, are either bigger than 0 or less than 0, you're at a saddle point, which means in some directions you go up and in other directions you go down. And if any of the eigenvalues are a 0, you could say nothing. That says if some of the eigenvalues are positive, then you point up in some directions. If some of the eigenvalues are negative, you point down in others, and you're sort of in this kind of situation, where there's some directions where you go up as you go out, and other directions that you go down as you go up. And then finally, the final case is if any eigenvalues are 0, HF, A are 0, then you can say nothing. You need to use different kind of analysis to do it. Usually that means the surface is too flat. So let's do an example. So top to bottom example of how to do this. All right. Okay, so let's look at f of xy equal to x squared plus xy plus y squared plus 2x minus 2y plus 5. Any idea what that is, by the way? You could probably tell me what that surface is just looking at it. Let's see. It has 2 squares in it, and they're both positive. Come on, man, you guys. It would be a circle if we had a fixed constant over here, but it's not fixed, right? This is a paraboloid. If you use completing the square, which you should all know how to do, if you use completing the square on this, you could sort this out into a paraboloid. Right? In fact, that cross term makes it kind of nasty. It's a paraboloid that's got an ellipse in the middle and it's kind of rotated. Okay, so let's find the critical points. How do I do that? What do I got to start with? I want to find critical points of this thing. Possible local maximum in. What am I going to do? df. Okay, so df is the x derivative, which is 2x plus y plus 2. And the y derivative, which is x plus 2y minus 2. Critical points happen where df is equal to 0. So critical points at df is equal to the 0 matrix. So 2x plus y plus 2 has to be equal to 0, and x plus 2y minus 2 has to be equal to 0. So that means y has to be equal to minus 2x minus 2, and y has to be equal to minus 1/2 x plus 1. Now what? That solves system equations, right? They're both equal to y, semi-equal to each other. Minus 2x minus 2 is equal to minus 1/2 x plus 1. I think you end up here with x is equal to minus 2 when you do the algebra. I hope I don't have to walk you through this kind of algebra, but I would if I had to. Anyway, it's a system of simultaneous equations, right? We need values to solve both equations to be critical points. They just solve this one, that says fx is 0. If they just solve this one, it means fy is 0. So both of them being equal to 0 at the same time is going to force this matrix to be 0. I think y is equal to 2 is the y value that comes along with that. So there's one critical point, and it's at minus 2, 2. Now what? Well, now I better compute the Hessian matrix, because I'm going to use the second derivative test. So the Hessian matrix, HF, is equal to the second derivative of f with respect to x. So I take, that's fx, and this is fy. So fxx is 2, and fxy is 1, and fyx is 1, and fyy is 2. Oh, that's pretty easy. Then I go to Wolfram alpha, and I type in the matrix. What's that? This is fxx, fxy, fyx, and fyy. I just looked at these and took the x derivative and the y derivative and the x derivative and the y derivative.
At point.
I haven't evaluated anywhere yet. All the x's and y's disappeared. So if HF is constantly equal to this, then it's also the case that HF at minus 2, 2 is equal to 2, 1, 1, 2. Kind of a silly example because it's got sort of constant curvature. Okay, so what's the matrix? 2, 1, 1, 2. Okay, which diagonalizes into trace determinant 3, 3, and 1. Lambda 1 is 3. Lambda 2 is 1. Are all the eigenvalues positive? You know what we should do instead? We should compute. Let's do Colley's method real quick. Here's what Colley says to do. What is the determinant of that? Well, a 1-by-1 matrix, you do determinant by just itself. Oh, that's positive. Now, what's the determinant of the matrix? Well, it's equal to 2 times 2 minus 1 times 1, which is 3, which is also positive. Since everything was positive, it must be the case that it was, she doesn't tell you, but that means all the eigenvalues are positive. So that sucks. Don't do that. You can imagine that if you had 3, you'd have 3 determinants to compute. There'd be a sequence of these things you need to keep track of. As opposed to saying, oh, look, there's 2 eigenvalues and they're both positive. If all the eigenvalues are positive, it bends up in every direction. So it's a local minimum. There's just no reason to bog yourself down.
So it's always going to be 2 the eigenvalues one.
2 eigenvalues for a 2-variable problem. There could be more if there were more pieces of the function.
Oh.
So I'm going to do another example here of a more complicated function, so we can see something with z's in it, so we can do a bigger computation, right?
Like, so it's like all eigenvalues are positive, so it's below the mean.
It's, yeah, all eigenvalues are positive, so it's concave up in every direction, which means that that critical point must be a local minimum. The eigenvalues tell you what the local curvature is. Curvature locally is always positive, so it's a local minimum. Actually, I was talking to Benini, and he was mad that he can't ever say this in any of his classes because when he teaches differential geometry, nobody knows linear algebra. Anyway, so this is kind of a sophisticated way of doing this. All right, so let's look at this. Here's another example. It's a more complicated one. F of x and y and z, oh God, is equal to x to the third plus xy squared plus x squared plus y squared plus 3z squared u. Okay, well, we can do the same thing. I mean, I might not be able to draw this anymore. I mean, if any of you guys can visualize things in 4 dimensions, I'd be happy to see you do it. This has 3 input variables and 1 output, but that doesn't mean we can't still find local maxes and mins, right? Now, points that make this value that comes out of this thing locally maximized or locally minimized. So the same approach is going to happen. We're going to compute df, which in this case is 3x squared plus, wow, there's a lot of x's here, aren't there? Plus y squared plus 2x. Not really. Okay. And then fy, which is 2xy plus 2y. And then fz, which is just 6z. Oh man, I don't want to solve this all for 0. So critical points happen where any of the following happen. 3x squared plus y squared plus 2x is 0, and 2xy plus 2x is equal to 0, and 6z is equal, well, at least that part's easy. Z is equal to 0, that's nice. From this, it is not hard to see that there are 2 critical points, he says. So let's just write down what they are. I mean, obviously 0, 0, 0 is going to work here because every term is everywhere. And if you put zeros in for every value, you get 0 out, right? So 0, 0, 0 definitely works. And then she also makes the assertion that you can kill off all of the additional terms here by doing this. That you get, this is supposed to be 2y. Minus 2/3, 0, 0. There you go. Algebra gets you that. I'm not kidding when I say, she said, literally, it is not hard to see that. That's the argument that she makes for this being a critical point. Now, we can just test it if you don't believe it, right? If you put in minus 2/3, 0, 0, certainly that's 0. And this has y's in both terms, so that's equal to 0. And so if you put 0 in for y here, you get 3x squared plus 2x is equal to 0. And that happens whenever x is equal to 0 or x is equal to minus 2/3. Right? That's what the algebra is. So these definitely check out that they make all these equations equal to 0. So for now, let's go ahead.
The second one then is plus 2 times negative 2 and 3. Or is it 2y?
It's a y. Yeah, it's a y. I caught myself because I looked at her answer and didn't believe it. That's because I badly transcribed. All right, so real quick, let's write down HF. HF is equal to fxx, which is 6x plus 2, fxy, which is 2y, and then 0, and then fyx, which is 2y, and fyy, which is 2x plus 2, and fyz, which is 0, and then 0, 0, 6. What's that? Yes. This is fxx, fxy, fxz, fyx, fyy, fyz, fzx, fzy, and fzz. One of the ways you can tell that you've done this correctly is if the matrix you go to is actually symmetric. These were symmetric to each other. These are symmetric and those are symmetric, which makes me at least believe that I did something right. That all the mixed partials are equal. Okay, now let's compute HF at the different values. What is HF at 0, 0, 0? Well, we get out 2, 0, 0, 0, 2, 0, 0, 0, 0. Okay, right there, I know that determinant is going to be 0. This is a diagonal matrix. It has an eigenvalue of 0. The eigenvalues of this are lambda 1 is equal to 2 and lambda 2 is equal to 0. What can I conclude about 0, 0, 0? Well, nothing. I got this problem here. Yep. Oh, yes, it's saved. Okay, so we can say something. All right, thank you. This is my bad. That's a 6. Sorry about that. That's even better. Lambda 1 is 2. Lambda 2 is 6. They're both positive. That means that they're both positive. So this is a local minimum because we're concave up in every direction there. Now this picture is lying to you because we're in 4 dimensions, but it's the best you can do. Concave up. I just have a mnemonic device where I think the eigenvalues being positive. What's that?
Where's your third eigenvalue?
There's actually lambda 1 is 2, lambda 2 is 2, lambda 3 is 6. There's a repetition of eigenvalues here. So like if you really want the full deal, it would be lambda 1 is 2, lambda 2 is 2, and lambda 3 is 6. Eigenvalues can repeat.
The reason we don't have to know how you punch in.
It's diagonal. Diagonal matrices, you can just read the eigenvalues.
Okay, everything around is 0.
Yep. All right, let's check the other one. HF at minus 2/3, 0, 0. Oh god. Okay. Put a minus 2/3 in here.
How do we get the minus 2?
Solving this, a critical point that came out of solving each of these equations for 0, right? I mean, this equation can only be true if x and y are both 0. This equation can only be true if z is equal to 0. This equation holds when y is equal to 0, and also when x is equal to 2/3. Really, there's no control over x here. If y is 0, this equation is 0, and x would be anything. So this equation says z is 0, and this equation says y is 0. But if z is 0 and y is 0, and you plug them in here, you can solve for the x values that you need. And it's 0 and minus 2/3. Okay, so the second critical point you put in and you find its matrix, which happens to be minus 2, 0, 0, 0, 2/3, 0, 0, 0, 6. You can go off and punch that into a calculator if you want. And it's going to tell you that lambda 1 is equal to minus 2, lambda 2 is equal to 2/3, and lambda 3 is equal to 6. What sort of point does that make this? The saddle point. Down in curvature down in the x direction, curvature up in the z directions. This is a saddle point. It's not useless because if you're doing an optimization problem, if there was a 0 somewhere in here, that would be useless. If you're running an optimization algorithm, one thing that happens with optimization is saddle points turn out to be really useful facts because they're places where the function flattens out, but they're not numerically stable because you can slide off of them. If you're trying to climb into a minimum, you just slide down the function until you land in the minimum. If you're at a saddle point, you've got a numerical routine that's trying to find it, you can't, because if you say, oh, just keep going down until we reach the bottom, well, if you slide off the saddle point off the side, then your function is going to shoot away to minus infinity. So saddle points are not numerically stable, even though in optimization problems, oftentimes you want to find them. I mean, the reason that you might want to find a saddle point, in case you don't know, is you might have something where you want to find a local maximum minimum. Jesus Christ. You'll find a local maximum or local minimum in just one of the variables, right? In just x or just y. But you're not going to be able to use a global minimum finder to do that as a saddle point because a global finder will not be able to land itself on a saddle point. Yep.
Do we go over?
No, but that's easy to construct one if you want to see it.
You want to see one?
It doesn't tell you anything. So like imagine you got a function that looks like this. F of x is equal to x to the 4th plus y squared. Now you should believe that this thing, yeah, so 0, 0 is going to be where the derivative is equal to 0. It's got one critical point. df is equal to 4x to the 3rd plus 2y. So it has a critical point only at 0, 0. But the problem is this x to the 4th is really crushed as you get down. So in the x direction, it's really flat. X to the 4th gets really flat here and x is equal to 0. So it kind of looks like a paraboloid, but it's really squished in the x direction and really steep as you go out towards infinity. So if you compute the critical point at 0, 0, and then you compute the Hessian matrix, you end up with, okay, what's the derivative here? 12x to the 2nd, 0, 0, 2. at 0, 0, that gives you the matrix 0, 0, 0, 2, and that has eigenvalues. Lambda 1 is 0, and lambda 2 is 2, which means the second derivative test can't, even though it's obvious this is a minimum, the second derivative test cannot tell you that. Because you have this 0 eigenvalue, which means it's too flat in one of the directions. That's essentially what a second derivative being 0 means. This function is too flat to say what's going on.
So that's a
This is like, this would be called ambiguous or useless. It means more analysis is needed. So oftentimes you get this by looking at a picture or by looking at neat points that are near to that point to see what's happening. Yep.
So we find critical points by activating.
Yeah. So here you would write y is equal to 0. Once you find the critical points, you build the HF, and then I'm going to post a sheet that shows you how to take this. Computing these you can do by hand. Actually, writing down what the HF is, you can just plug values in. Right. All I did here was I put in the 0, 0 to figure out what its HF was. Right. This is HF at 0, 0. And then I'm going to post a picture of how you take this, or a little video of how you take this matrix and put it into Wolfram Alpha or Mathematica to figure out what the eigenvalues are. Or even most of you have calculators that will do this. Yeah. So the eigenvalues are the next move here, right? Which is, I don't really want to go through having you guys do eigenvalues by hand. You should be able to use eigenvalues. I don't care if you know how to make them. Yeah.
So if one is 0 and another left 0, and
Concave up, concave down. Saddle point. Yep.
and these are both 0 is
Concave up in both directions, which means it must be at the bottom of a well. Yep. All right. Thanks, guys. We're going to move on to integration next time. So everybody bone up on your integration here. Oh, so much integration coming. Triple integrals, double integrals, surface integrals, parametric integrals, integrating. No, why is everyone shaking their head at me?
Yes, we are.
Thank you.